Good afternoon. I am Dr. P. Usha Rani, Professor EEE Department, RMT Engineering College. Now I am going to brief about the topic of solid state drives, rotor resistance control of induction motor. Here if you consider torque equation, first equation as torque equation, which is directly proportional to rotor resistance. Second equation as maximum slip, which is directly proportional to rotor resistance. If you consider torque, maximum torque or the braking torque, if you consider, which is independent of rotor resistance. Okay, so if you take care of the relationship between maximum torque and the rotor resistance, which is independent. In this case, if you take care of your, by increasing your rotor resistance for a value of torque, for the same torque value, your speed goes on decreasing. Okay, if I increase my resistance, rotor resistance, for the same torque value, my speed goes on reducing. So here the advantages of this method, if you consider high motor torque capability, like V/F control of induction motor drive, high motor torque capability, and the cost is very low. If you take care of the drawbacks in this method, we have additional resistor connected in the rotor resistance, so I square R loss will be more and the efficiency will be reducing. This type of rotor resistance controller is useful in cranes, wall unit drives. Okay, so if you consider, this will be useful for smooth stepless control. So the circuit diagram for whatever I am showing here is static rotor resistance control. See, the rotor resistance can also be varied steplessly using this circuit diagram. Here if you consider, your stator is connected to 3-phase AC supply and the rotor circuit output voltage. Okay, voltage is connected to bridge rectifier through the inductor LD to the parallel combination of one transistor and the resistor R. So how you are varying your pulse width of this, the firing angle of this transistor, if you vary, or you can say the duty ratio here, for by varying the duty ratio of this transistor, you can have the control of your resistor value, that is rotor resistance value. So what is the purpose of this inductor is to reduce the ripple content in the DC circuit, to reduce the ripple content. So this is the current waveform, rotor current. Okay, by seeing that waveform, you can write the equation of rotor current as square root of 2/3 into ID, or ID as square root of 3/2 into IR. And then you can calculate your average value of resistance RAB in between the terminals A and B. Okay, which is 1 minus delta into R, where delta is the duty ratio of the transistor. By varying the duty ratio, you can have the control of rotor resistor. And if you calculate your power across the terminal A and B, ID square RAB, I am substituting ID value as square root of 3/2 into IR. So it will be, if I substitute that, I am getting 0.5 or 1 minus delta into IR square. I am taking the average per phase value, that is power consumed by resistor RAB per phase as 1/3 of PAB. So if I do that simplification, my answer is 0.5 R into 1 minus delta into IR square. So the total rotor circuit resistance, if you consider per phase value as, already rotor resistance RR is there, plus the additional resistor connected across the transistor as 0.5 R into 1 minus delta. I already mentioned delta as the duty ratio of the transistor. You can vary your RRT. If I can consider delta has changed, delta 1 if I consider, this 1 minus 1 is 0, so I am getting only RR. Okay, so when delta is 1, I am getting the RRT is equal to only RR. If delta is 0 means I am getting the answer of RRT as RR plus 0.5 into R. This is the value. So the major advantage, high torque capability characteristics. Like this method which will be useful for what Leonard drives. Okay, intermittent load application you can use. So the main thing here, low cost, high torque capability characteristics. Thank you.